Now that we've learned about the 8 primitive data types, let's go ahead and start using them in code. So as you can see, I've already created a Java file called 8 primitive data types. So I'm gonna go ahead and create the class. So public class 8 primitive data types, open close curly braces, and let me add in my method header. So public static void main string array arguments. All right, and don't forget to put our info up top. All right, so we learned that there's 6 primitive data types for numbers. We have 4 for integers and 2 for floating point. Okay, floating point is simply just another way of saying numbers with a fractional part, with a decimal fractional part. So we have the float and the double for the floating point values, and we have the byte, the short, the int, and the long for the integer values. So what I'm going to do is I'm going to go ahead and create those 6 variables to hold those types of numbers. The other 2 types of primitive data types, as we've learned, was the Boolean and the char. Okay, so the very first integer that we have, which is the smallest, is the byte. And I'm just going to name this, let me see, we'll just call it like num1. Will be real generic. And then the short, which is the second smallest integer, is num2, and then the int, num3, and the long, which is num4. Okay, now we've learned from the lecture that the byte is 8 bits. And the short is 16. The int is 32. And the long is 64. Now the way that Java works is whenever we type in an integer into the program, it's going to see it as an int. Okay, so if I type in like 54, then it's going to see it as an int. Okay, so num1 we can say is 54. Now Java is saying this as a 54-bit, it's saying 54 as a 32-bit integer, but because we're assigning it to a byte, it's automatically going to convert it down to 8 bits if it falls within a range. Now 8 bits, we can only go from negative 128 to positive 127 because there's only 256 possible values for a byte. So we can just write what we can call a byte literal by just typing an integer within the range of a byte. Same thing with a short. If you put num2 is equal to, let's see, 1,000. That's in the range of a byte, and that is in the range of a short. And if you write num3, it could be any number as long as it's in the range of an integer, then Java is going to be okay with it. So let's just say that's 1,000,000. That's 1 billion. All right, and then num4. Now this here, num4 is a long, and it can be a really big number, but let's just go ahead and say this. Now Java is going to see this as an integer, and it's going to complain because it's going to say that it's too big for us. So if we want to actually say that it is a long, we're going to have to put an L, lowercase l, or capital L at the end of it. But let's just go ahead and see what happens as we leave it like that. So I'm going to go ahead and save this, and I'm going to compile. And we can see that we get an error. Let's see what the error is. So integer value is too large. Okay, so it knows that this is 10 billion. Okay, because I put enough zeros to make this value right here 10 billion. So it's saying that it's trying to make that an integer, but it's just the number is too big for it to be an integer. We have to tell Java that that is in fact a long. So we're going to put a capital L at the end of it. And now when we go to compile, we can see that there's no problems. It's still thinking. All right, finished. So let's go ahead and just output these numbers really quick. So system.out.println say num1 is num1. All right, and then I'll change this to 2, 3, and 4. 2, 3, 4. All right, so save this, compile, and run. All right, and you can see that the values did in fact get stored into our integer variables and they were printed out. Okay, now the same, like, so what do you think will happen if we made this byte out of this integer out of range of a byte? To say we know that the highest possible value is 127. So if I put 128 and I try to save and compile, Java knows that 128 is out of range for a byte, so it sees you want to store this into a byte, but it's making this an integer. And the reason why is because it's out of range for a byte. But if you make it 127, which is in range, then when I compile, you'll see that everything is okay, right? And I can run the program. Okay, so we use the L if you want to use a long literal in Java, and everything else is an integer. If we wanted an integer to be a byte, we just have to put it in range. If you want it to be short, we have to put it in range. So a short is, I can't remember what the highest possible value is, but it's like 32,000 or something like that. So if I were to go to 100,000, then Java will complain. Okay, because that number is out of range for a short, right? So 16 bits cannot represent that number because Java uses, it's going to divide the possible values between negative and positive, and it won't be able to actually represent that value using 16 bits. So we have an error there. It couldn't convert it. It couldn't convert that integer to a short, so it's complaining about how big that number is. All right, so now let's talk about the float and the double. So we'll say float is num5, and this is also 32 bits. And we have a double, which is num6, and this is 64 bits. Okay, now these are different than the integers because they can represent fractional values. So if I come down over here and I say, okay, well, num5, which is a floating point value, I'm going to assign it 1.7, and num6, I'm going to assign 1.7. When I go to compile, I run into a problem. Okay, and the problem is, I didn't change num2 before. Dang it. All right, let me recompile. And the problem is that 1.7 is seen as a double. Okay, now a double is 64 bits, and we're trying to put that into a 32-bit float. So anything with a decimal, Java will automatically see as a double. So it's going to use 64 bits to represent it. It doesn't downcast, even though 1.7 is in the range of a floating point. So with the integers, we were able to do that as long as 120, as long as the byte value was in the range of a byte, like 127, everything was okay. But it's not the case for floating point values. So if I want to make that literal value a float instead of a double, what I need to do is put a lowercase f or a capital F at the end of it. Okay, so once I do that, when I go to compile, I'm going to use Control-1 to compile. You'll see that everything's okay. And then when I go to run, actually before I run, let me go ahead and print these values out. All right, save and compile and run. And then when I compile and run, you can see that num5 and num6, they both have the same value. The only difference is behind the scenes is num6 is holding a 64-bit value while num5 is holding a 32-bit value. So this is how we write what we call a float literal, is by using the lowercase f or the uppercase f. It could be lowercase or it could be uppercase. Okay, now the next thing I wanted to show you is the difference between the integer, which is 32 bits, and the float, which is 32 bits. Now you might assume that since they're both 32-bit values, that you can assign a float to an integer, but that's not the case, because a float still has a higher resolution, if that makes sense, meaning the float can retain the decimal places while the integer does not. So if you try to assign a float value to an integer value, then Java will complain. Okay, so let's go ahead and test that out. So after I print out my initial values, I'm going to come down here and I'm going to say, okay, well, num3 I know is an integer, and I want to assign it 2.4f, which is a floating point value. And then I want to print out my value of my integer. So I'm going to go ahead and just print it out to the console right there and compile, Control-1. And I already get an error. Let's see what that error is. Okay, so it's telling you incompatible types, possible loss of conversion from float to an int. You can see the message there. So that's just Java's way of saying, hey, look, you have this floating point value that has decimal places. This is a 32-bit floating point value, and you're trying to assign it to a 32-bit integer. I know that they're both 32 bits, but you're going to lose your decimal places. So there is a way that you can actually assign those values. We'll talk about that later in the chapter, but the way to actually do that is by converting that value to an integer by casting. Okay, now when you're using a literal, we're just gonna have to just use a literal integer, meaning like just use a 2 instead of using 2.4f. Okay, or you can put that in parentheses and then cast it to an int like so, and Java will be okay with this. Okay, it's just basically saying, you know what, convert that floating point value to an integer. That's like, this is what we call casting. So we're forcing this value to be an integer. So when I compile and run, you see that the number is just 2. Okay, but to me, it makes no sense doing this. If you're typing out a literal value for an integer, then you might as well just put the value that you're actually wanting, meaning to me, that makes no sense. Just put the 2. Okay, now if you wanted to actually put a floating point value from a variable, then that is a different case. Okay, we know that our float value is stored in num5. Okay, now when we go to compile, right, we get the same error. Right, Java knows that this is a float, this is an integer. You're trying to convert something that retains the decimal places to something that doesn't. So if we want to actually force this to an integer, then we will. Now it only forces that value to an integer on that line, so the value is not going to retain in num5. It's just going to convert num5 to an int, right? Whatever, it's going to convert that value of num5 to an int and store that value inside of num3. But after that line, num5 will retain its value. So let's print this out. All right, so compile, Control-1, and then run, and then you can see that I did take the value from num5 inside of my num3, which is an integer, and I still retained the value that was in num5. So it still had 1.7 even after this line. It just, at this moment, it just took that value and converted it to an int and then stored the result inside of num3. So this is the 6 numeric primitive data types. Now there are 2 more. We have the Boolean, which we'll talk more about in chapter 5 and 6. We're going to use it to control loops. So we'll just say bool and then Boolean, and we'll just say like bool1. And this could only be true or false. And then we have our chars. I'll just say like my char. Now the char is a little different. Okay, now it kind of works like the string, meaning you can assign a char literal, but it only takes in 1 character. And as we discussed, the single quote is what specifies a char literal. So if I want just to store 1 character inside of my char, and chars can only store 1 character, I just use a single quote and a value. Okay, M. So let me just print out these values. All right, so compile, run, and you can see my values that I printed out. Okay, now the unique thing about the char also is that you can assign it a number, okay, and that number is going to be whatever value is stored at that specific location in the Unicode character set. So let's just say if I looked at the Unicode character set from the back of the book in the appendix, and there's a character that I wanted to print out, and for some reason I didn't want to write out the actual literal value. I wanted to write out the numeric entry for it inside of the table. Let's just say, I'm not sure what value I'm going to print out, but let's just say 123. Let's see what's at 123. So I'm going to save this and compile, run, and the open curly brace is what's at 123. I don't know if you guys see that, but that's what character in the Unicode character set. So if you look at the Unicode character set, in the location of 123, there is the open curly brace. Okay, so this could be any number. If you are going to use an int variable, meaning, you know what, let's just go ahead and take whatever is in num3 and assign it to our char. In this case, you're going to actually have to cast that value, because Java is going to see this as an int and this is a char, and it's going to complain about it. So I can go to compile, and you can already see that there's a compilation error. Okay, and it's saying you're going from an int to a char. So what we need to do is we need to cast that. And the reason why you have to cast that is because it's 16 bits, the char. So let's see what happens if we use a short here. If we use a short instead of a char, or excuse me, we use a short instead of an int. We save and we compile. Now we still have the same problem, okay? And the reason why there isn't a direct conversion is because the Unicode character set doesn't have any negative values for the numbers, right? So even though the char can hold 16-bit number for the specific character that you're going to look up, it doesn't actually include the short, okay? Because the short could be negative. So let's if you actually wanted to take whatever value is there, you're going to have to just come over here and cast it to a char. Okay, now remember that the char is a 16-bit and the short is also a 16-bit, but it's the same way between the float and the int, okay, where, you know, the float has a higher precision because it can retain fractional part where the int can't. So like Java notices, hey, look, you're going to convert these two values and you're going to lose your precision. Now, the difference between the short and the char, even though they're both 16 bits, is that this short can go negative, meaning it retains negative values, where the char, right, the values in the Unicode character set, the entries, right, they don't go negative, right? You start at 0 and then you go to like 65,000 something, okay? You don't actually go negative. Now with the short, you start at negative 32,000 to positive 32,000. So the range is different. So you can have a negative value in a short, and you can't have a negative value for a char for the entry inside of the Unicode character set. Okay, well that is just a little bit beyond the scope of this class. But just know that the Unicode character set does not contain negative entries, meaning it starts at 0 and it goes to positive 65,000. Right, but the entries in those tables where those indexes are can be negative numbers, if that makes sense. If it doesn't, just go ahead and read the back of the appendix that talks about the Unicode character set. It explains like in detail like the range of values that it contains and the entries inside of the tables. Okay. Now, one more thing I wanted to show you, which I'm going to include things that are beyond the scope of Chapter 2. But let's just go ahead and print out a bunch of chars using a for loop. Okay, so I'm going to just cause a line. You know, before I do that, I don't think I actually fixed and compiled what I was doing. So let me just delete this really quick, hop back up to the top. And okay, I did convert that to a char. So let's go ahead and compile, And it hasn't been initialized. Okay, so I did this after I didn't even see that error. I apologize. But what's happening now is it's saying num2 might not have been initialized, meaning like it was never set to some value before. Okay, so let's just go ahead and set it to 56. Okay, and now we assign it here, and let's go ahead and print it out. Is it being printed out? It is still being printed out. So I'm gonna go ahead and compile and run, and I assigned it whatever value was in num2, which is 10,000, and my char is 8. That doesn't make sense to me. Oh, 56. Okay, I'm sorry. I thought I saw 1,000. Okay, I'm totally confused right now. Okay, so my char had the value of 56 in the Unicode character set, meaning whatever value is at spot 56 is the value that it's printing out, and the value that it printed out was 8. So that means 8 is at spot 56. So we can make the assumption that 9 is going to be at spot 57. Now the reason I got confused is because when I came over here and looked at what was in num2, it said 10,000, but I forgot I declared my variables for first before I actually did any initialization. I did initialization after I assigned my char whatever value was in num2, in which I put a 56, or previously put a 56, but this time a 57. So let me compile, run, and now you can see that my char is 9. So at spot 57 in the Unicode character set, 9 is a character. Now, if you go outside of the range of allowed characters for your operating system, like I don't have any international characters installed on my computer, but if I just did like 12,000 and I compiled and I run, I will get this question mark, and that's just command prompt's way of saying it doesn't recognize the character. There's actually some weird international character there, but it just doesn't recognize it, so it just puts a question mark. Okay, so it's not truly a question mark there. There is some valid character. You can go online and read up on the Unicode character set and actually grab that value at that location to see what it's supposed to be, but in this case we don't actually see it. All right, so one quick thing that I wanted to do is just write a for loop really quick and just print out a series of values so you can see all the different spots of what characters at the Unicode character set. So some of these values are going to be blank because there are some blanks and like line characters, interiors tabs, things like that, backspace, carriage return. These are all characters inside of the Unicode character set. So let me go and just create a quick for loop so I can show you these values. So I'm just going to go ahead and print line there. I'm going to say for, let's say int x is 0. All x is less than, and we'll just go to 200 for now. I'm just, we'll say x plus plus, and we'll talk about loops in chapters 5 and 6. Okay, so what I'm going to do is I'm going to say char c is equal to whatever value is at x. So you're going to start off at 0, and we'll say system dot out dot print line, and I'm going to print out c. Actually, no, I'm going to do this. I'm going to print out the location and then the value. So we'll say x plus and then the value c. All right, and let's compile this, control 1, and run, control 2, and it's printing out all these characters. So there are actually some that are valid. So there's like these weird looking A's, but there are some question marks right toward the end of this, meaning it can't figure out what those values are. There's like this character, which is like an upside down question mark. There's like some fractions there, but if you go up to the very top, okay, there are all of these characters here, right? So this is kind of like a line space or a line break. There was one of them was actually a sound character. I did hear a noise play. I forget which one it is. I don't have all this stuff memorized, but the first 128 entries do come from the ASCII character set. So symbols look they start off at 32. Like there's some space, exclamation mark, and then there's a bunch of symbols, numbers start off at 48, and so on and so on. Now it's kind of important to note here that capital letters actually come before lowercase letters. Right, those are all the capital letters. They start off at 65, and the lowercase letters will start off at 97. Right, and there's some symbols here as well. And past 128, we're out of the range of the ASCII character set. And then there's a bunch of question marks here. I'm not sure what's supposed to be there. I don't have all this stuff memorized. But if you're interested in that, there's plenty of resources online. And you also have the appendix in the back of the book. And that is it for primitive data types. I know Boolean might still be mysterious right now, but in chapters 5 and 6, trust me, we're going to be using it a lot. Okay. 2 states, either true or false. It cannot be anything else. As mentioned in the lecture, some other languages let you use 1 or 0 for values of true and false, but Java strictly just stuck to true and false for accepted values for Booleans.